as you can read, the title is Some Recent Results on the Theory of Group Equivariant and Non-expansive Operators, GENEOs in brief, and its application to machine learning. My plan is like this. I will start by giving 10 slides where the epistemological view of this topic is given. So no mathematics in these 10 slides. Then I will speak about some topological arithmetic basics for the theory of group equivariant and non-expansive operators. Then I will speak about ways to build group equivariant and non-expansive operators. And finally, I will give you two examples of applications of these operators in machine learning. So I start from data. I will give you some remarks. You can share these remarks, this opinion or not. These are the basics of this approach to machine learning. First of all, we have to say that data can be often regarded as functions. Not in any case, but in several cases, we have that data are functions. For example, when we consider an electrocardiogram, this can be seen as a function from the real number to the real number. A gray level image can be seen as a function from the real plane to the real numbers. And the computerized tomography scan can be seen as a function from a helix going around a body to the real numbers. Maybe you can think, okay, but there are plenty of things that are not functions. This is true, but please consider that, for example, if you consider a graph, when you take the adjacency matrix, it is a function. It is a function from the set of cells to, let me say, the set 0, 1, of, or in case of weighted graphs, to the interval, the closed interval 0, 1. So a graph can be seen as a function. And if you take a cloud of points in the real space or in Rn, well, this is equivalent to the distance function. That is the function taking each point of the Euclidean space to the distance from the cloud of points. And this information is equivalent to the cloud of points. So in several cases, data can be represented as functions. I will focus on functions from sets to the real numbers, but the theory can be applied to Rk-valued functions. Now, data are processed by observers. If we have no observer, there is no, I could say, no meaning for data. We need observer elaborating data. And an observer is an agent that transforms data, usually accordingly to some rules. For example, in this talk, I will speak about, let me say, equivariant operator and non-expansive operator. So there are some properties of observers that are mostly important, at least in this talk. Another remark that is important is that observers are variables in data analysis. We have to choose the observer in order to ask questions about data. If you change the observer, you change the interpretation of data. Data interpretation strongly depends on the chosen observers. Okay, I have also to say that our interest in data is greatly overrated. We are hardly ever interested directly in data, but in the reaction of the observer to the presence of data. For example, I have a skin lesion on my arm. Okay, I have this skin lesion, and I could be worried about that. I can take a picture of this skin lesion, but I'm not interested at all in this picture. What I am really interested in is the reaction of my dermatologist to this data. So the reaction of the observer. And the same holds for almost any kind of data. We are mostly interested in the reaction of the observers to the presence of data, not directly on data. Another important remark is this one. Generally speaking, there is no structure in data. The structure of data is a projection of the structure of the observer. You choose an observer, and the observer projects some structure on the data that is part of the interpretation of the data. This is quite important. There is no absolute value in data. Observers are often associated with invariance groups. For example, if you are interested in comparing images of shells, maybe you will consider the group of isometries of the real plane, since you wish to consider this shell, this image, equivalent to this one. But if you are interested in letters, you don't want to consider these two letters the same. They are different from each other, and so you are changing the invariance group. In this case, probably you will judge more suitable the group of translations or maybe deletions. Okay, so how can we represent observers? Observers are structures able to change data into other data, and usually do that by respecting some data equivalencies, that is, by commuting with some transformations. For example, think about blurring an image. You have an image, and you compute the convolution with a symmetrical kernel, okay? I mean a rotationally symmetrical kernel. In this case, you have the group of isometries of real plane commutes with a convolution. You can compute a convolution, and then you can rotate and translate the image, or you can do this in the reverse order, and you get the same result. So in this case, you are stating that the operator commutes with a group of transformations, in this case, a group of isometries of the real plane. As a first approximation, observers can be represented as group equivariant operators. They are machine to change functions into other functions, and they do that accordingly to some kind of equivariance with respect to some kind of group. But in this talk, I will speak about the theory of group equivariant non-expansive operators, GENEOs, not just GEOs, group equivariant operators. Why non-expansive? There are two reasons. The first one is that observers are often assumed to simplify the metric structure of data in order to produce meaningful interpretation. This means that you have to not increase the distance between objects. You have to decrease the distance. The operator must be non-expansive. This from the epistemological point of view. From the mathematical point of view, we can see, and we will see that in the next slides, that non-expansiveness guarantees good topological properties, mainly compactness. So after these 10 slides, making clear the epistemological approach I am presenting here, I go to say something about the topological metric basics for the theory of GENEOs. I will do that by giving by citing 4 papers that represents and describes some recent results about the theory of GENEOs. I start with this paper, Towards a Topological Geometrical Theory of Group Equivariant Non-Expansive Operators for Data Analysis and Machine Intelligence. In this paper, the mathematical foundation of the theory is given, and I'm going to give you, let me say, some basics about this theory in the next slides. If someone is interested in these results, okay, the slides are available on my web page. You can click on the link here, and you can download the paper if you are interested. Okay, the first statement is that all begins with a space of admissible functions. Admissible functions are the measurements that we consider acceptable, admissible in this game. Okay, for example, if I am interested in electrocardiograms, I'm interested in periodic, almost periodical functions from real numbers to real numbers. But these functions must be bounded, and I do not accept as an electrocardiogram the exponential function. So I have a set of admissible signals, admissible functions. So let X be a non-empty set. Let phi be a topological subspace of a set of all bounded functions from X to real numbers, endowed with a topology induced by the max norm metric. Okay, so we have this way of comparing data. We can see X as the space where we can make our measurements, and phi as the space of all possible measurements given by our measuring tools or our observers giving us their measurements. We will say that phi is a set of admissible functions or signals. In other words, phi is the set of all functions from X to R that can be produced by our measuring instruments or by our observers. For example, a gray level image can be represented as a function from the real plane to the interval 0, 1. In this case, X is the real plane. Perception pair. What is a perception pair? Let us consider a group G of bijections, that is permutations of the domain X, such that with this property, if you take an admissible signal phi and you compose phi with an element of our group, you get another admissible function. We say in this case, and only in this case, you say that phi G is a perception pair. The choice of a perception pair states which data can be considered as legitimate measurements, the function in capital Phi, and which group represents the equivalence between data, the group G. To proceed, we need to introduce suitable topologies on X and G. At the beginning, X has no topology and G has no topology. Before doing that, we recall that the initial topology on a set with respect to the set of functions phi is the coarsest topology in X, such that every function phi in capital Phi is continuous. This is the initial topology. Let us define on X the pseudometric dx. This is just this number. When you compare 2 points in the domain capital X, x1 and x2, the pseudo distance between these 2 points is the supremum, varying the admissible signal of the Euclidean distance between phi of x1 and phi of x2. Pseudometric just means that you remove the assumption that you have for metrics that when 2 points have a vanishing distance, they must coincide. This is not true for pseudometrics. So what does it mean? The use of dx, this pseudometric implies that we can distinguish 2 points only if a measurement exists, taking those points to different values. So what is the epistemology under this choice? If you have 2 objects, but they have the same color, the same position at the same time, the same size, and so on, and you have no way of distinguishing between them, there is no way of giving a positive distance to the pair given by these 2 objects, okay? If you choose this pseudometric dx, you assume this epistemological view of a problem. The topology associated with this pseudometric is finer than the initial topology on X with respect to the set of functions capital Phi. If the set of admissible functions capital Phi is totally bounded, then this pseudometric coincides with the initial topology. So any function capital Phi becomes continuous. Since we have theorem, every function, this is trivial, every function in capital Phi is non-expansive with respect to our pseudometric, and thence is continuous. Maybe the function is not continuous with respect to the Euclidean distance, but it is indeed continuous with respect to our topology. If phi, another theorem states that if capital Phi is compact and X is complete, then X is compact. Please consider that we can always make X complete. So we can, if the set of data is compact, then we can always assume that with respect to our topology, the domain of the data of a function is always compact. In the following, we usually assume that our set of data is compact and X is complete and dense compact. Now, some magic happens. Each bijection is an isometry when we consider this setting. Indeed, if we consider the group of phi preserving bijections, phi preserving means that when you compose your signals with any element of a group or the inverse of this element, U stays in capital Phi. And if you consider the group of phi preserving bijections, the group of phi preserving homeomorphisms, and the group of phi preserving isometries, they coincide. And this depends on our choice of a metric dx. So let us now focus our attention on a subgroup G of a group of all phi preserving homomorphisms of X, or if you prefer, isometries, or if you prefer, bijections. We can define the pseudometric dg on G by setting that the pseudo distance between two permutations, G1 and G2, is the supremum varying the signal, the admissible signal, of the max norm distance between phi composed G1 and phi composed G2. If you, for example, if you take just constant function, there is no way of seeing the difference between the permutations by using your measurements. So you have to accept the idea that the pseudo distance between two permutations is always zero. This is true just in case you take just a trivial set of functions, the constant functions. But this is not true, of course, in general, in usual applications. Theorem: G is a topological group with respect to this pseudo distance, and the action of a group on the set of admissible functions by right composition is continuous. And we also have that if the set of continuous of our admissible functions is compact and G is complete, then G is compact. A collaborator of mine has shown, Dr. Farad Samad, that you can always complete G. And also every structure you can introduce in this game. So you can assume that if phi is compact, then the group is always compact. Everything comes from the measurements in this game. You have no structure on X and the group. You put a structure, inheriting the structure from the set of measurements. Okay, now I can introduce the concept, formally introduce the concept of group equivariant operators and group equivariant non-expansive operators, GEOs and GENEOs. So we have perception pair. I recall that each pair phi G with G subgroup of a group of any possible phi preserving homomorphism of a domain X is called a perception pair. Let us assume that two perception pairs phi G and psi H are given and fix a group homomorphisms T from G to H. So you have a way to translate the action of G on phi into the action of H on psi by means of this homomorphism. Each function f from phi to psi, such that this equality holds, that is, the operator f commutes with the action of the groups for every admissible signal phi and any element G in the group, is called a group equivariant operator, a GEO, associated with the homomorphism T you have chosen. If f is also non-expansive, so the distance under the action of f, the distance between data does not increase, then f is called a group equivariant non-expansive operator, a GENEO, associated with T. Now, I want to give you an example of GENEO. So please consider that we are interested in the distribution of temperatures over the Earth. So in order to model the Earth, we have S2, and we have a map taking each point of the Earth of S2 to a temperature. And when we speak about, we consider a temperature, we consider a number in a closed interval AB, where A is the minimum of the possible temperature that we can measure on the Earth, and B is the maximum, okay? Think about minus 100 degrees and plus 100 degrees in order to be sure that your values belong to this interval. Now think that, consider that we cannot recognize countries on the sphere. We can just recognize the North Pole N and the South Pole S. Now, let us consider these two perception pairs. Phi G is like this. The domain of our functions is S2, X is S2. Phi, the set of admissible functions, is the set of one Lipschitz functions from S2 to our interval AB. G is the group of rotations of S2 around the axis, North Pole, South Pole. Okay? And there is another perception pair that is given by the domain Y is the equator of the Earth, and is S1, can be modeled as S1. Psi is the set of one Lipschitz functions from S1 to the interval AB, and H is the group of rotations of the equator. Now we can consider a GENEO. The role of the homomorphism T is quite natural in this simple example. We associate each rotation of the Earth of alpha degree to the rotation of the equator of the same number of degrees. Okay, so this homomorphism in this case is indeed a isomorphism. Okay, what is F? By definition, F take a distribution of temperatures phi over the Earth to a new function psi that is defined on the equator. Psi takes each point y belonging to the equator to the average of the temperatures along the meridian containing y for every distribution of temperatures over the Earth. We can easily check that F verifies the properties defining the concept of group equivariant non-expansive operator with respect to the isomorphisms T. In plain words, our GENEO simplifies the data by transforming temperature distributions on the Earth into temperature distributions on the equator. By doing that, you are forgetting a lot of things, but you are simplifying the data. And you do that in an equivariant and non-expansive way. Now we have two key results and two good news for applications. Let us assume that our homomorphism T from G to H has been fixed. Let us define a natural metric, the GENEO, on the set of all GENEOs from the first perception pair phi G to the other perception pair psi H. We do that by setting the distance between the two GENEOs F1 and F2 equal to the supremum varying the admissible signal of the max norm distance between F1 of phi and F2 of phi, quite natural. Two theorems. The first theorem states that if phi and psi are compact, then the set of any possible GENEOs is compact too. And if psi is convex, then the set of GENEOs is convex too. Please consider this. The assumption that the compactness of phi and psi implies the compactness of a set of observers is not completely natural and obvious. Think about this. In real life, we usually consider data and observers on quite different levels. And maybe we can have cases where data are quite simple and observers are quite complex. For example, I can consider a simple object on the table. The object is trivial. I'm not trivial as an observer. But another condition can be thought of. Think about me looking at the universe. The universe is much more complex than me. And in this case, the level of complexity of data and the observer is reversed. So there is no reason to assume that the compactness of data implies the compactness. Compactness implies approximability, finite approximability. There is no reason to say that the compactness of data implies the compactness of a set of observers. But if we take our structures, the structure I'm thinking about in this theory, we have this theorem. If data are compact sets, then the set of all observers is compact too, and thence finitely approximable. Two key observations. While the space of data is often non-convex, and thence averaging data does not make sense, the assumption of convexity of psi implies the convexity of a space of observers and allows us to consider the average of observers. So this is important in applications. Another key observation is this one. Our main goal is to develop a good geometric and compositional theory to approximate an ideal observer. For example, in application, the ideal physician looking at the result of examinations, tests, and so on. In our model, approximating observers means to look for a GENEO-F that minimizes a suitable cost function. The cost function quantifies the error that is committed by taking the GENEO-F instead of the ideal observer. Since the space of GENEOs is compact and convex, under the assumption that the data spaces are compact and convex, if the cost function is strictly convex, we have that there is one and only one GENEO that best approximates the ideal observer. Now, after giving just some basic view of the theory of GENEOs, I'd like to show that GENEOs indeed exists in the sense that we can build them. And so I'm going to illustrate some results proved in this paper on the construction of group equivariant and expansive operators via permutants and symmetric functions. There are some trivial ways of building GENEOs, and the first result you can think of is composition. If you have two GENEOs and you compose them, you get another GENEO. Of course, with respect to the composition of the homomorphisms. If you take a one Lipschitz function from Rn to R, let us call this function L, okay? And you composed n GENEOs by using L, these one Lipschitz functions, you obtain another GENEO with respect to the common homomorphism that is shared by the n GENEOs. Our trivial results are given the next three propositions that trivially follow from the proposition concerning the one Lipschitz function. First of all, GENEOs are a lattice. There is a lattice structure on GENEOs, since the maximum of GENEOs is still a GENEO, and the minimum of GENEOs is still a GENEO. Then, when we translate a GENEO, we obtain another GENEO. And when we consider, this is a trivial consequence of a theorem about the convexity of a space of GENEOs, when we consider the convex combination of GENEOs, you get another GENEO. This is quite important in applications. The convex combination of GENEOs is still a GENEO. These are trivial results, okay? Now I'm going to show a non-trivial result. This result is another method to produce GENEOs that is based on permutant measures. Let us now consider the set phi of all functions from a finite set X to the real numbers, and a subgroup G of a group of all permutations of X, okay? A finite definition, a finite signed measure mu on the group of all permutations of X is called a permutant measure with respect to the group G if every subset H of this group of permutations is measurable and mu is invariant under the conjugation action of G. So we have this equality here. The measure does not change when we apply conjugation. If we have this, if we have a permutant measure, we can build a geneo with respect to the group G. Proposition: if mu is a permutant measure with respect to G, then the map F mu, defined by using this formula, is a linear geneo. In practice, we associate with each function admissible signal phi an average of the function phi composed the inverse of H, weighted with our permutant measure, where the summation is for any permutation of X. Maybe you can think, but the group of permutation is huge. It is true in many cases, but in many cases we can also have that the support of a permutant measure is quite small. And so this summation is restricted to a small set. I have to add in the proposition that if the total mass of our permutant measure is less than 1, then F mu is not just a group equivariant operator. It is indeed a group equivariant non-expansive operator. So we have a method to build GENEOs. Now an example of permutant measure. Let us consider the set X of the vertices of a cube in R3. So we have 8 points, a set with 8 points. This is a trivial example of permutant measure. We have X with 8 points. And the group G is the group of orientation preserving isometries of R3 that take X to X. Now, let us consider the 3 planes, pi1, pi2, pi3, that you can see in the picture. They are the planes that contain the center of mass of the cube and are parallel to a face of a cube. Let HI be the orthogonal symmetry with respect to pi I. So we have a symmetry with respect to this plane, the symmetry with respect to this plane, and the symmetry with respect to this plane. We can now define the permutant measure mu on the group of all permutations of our set of 8 points by setting mu of H1 equal to mu of H2 equal to mu of H3 equal to C, where C is a positive real number. And you take, you state that the measure of any other permutation is 0. Now, what is the support of this permutant measure? The cardinality of this support is 3, just 3 permutations, while the group is made of 24 permutations. Please consider that the support of the permutant measure is not a group, it's just a set. Now, we have a way, by using permutant measure to build GENEOs. It is interesting to observe that the set Pm of G of all permutant measures with respect to G is a lattice. Not just the set of GENEOs is a lattice. All the set of permutant measures is a lattice. Indeed, if mu1, mu2 are permutant measures, then the measures mu prime and mu second on the group of bijections of X defined in this trivial way still belong to the set of permutant measures. The absolute value conserve the property of being a permutant measures, and furthermore, the set of permutant measures is closed under linear combination. So it has a natural structure of real vector space. We stress that when the group G becomes larger and larger, the lattice of the permutant measures becomes smaller and smaller, since your request is stronger. In other words, the theory of permutant measures becomes more and more useful and interesting as the groups get bigger and bigger. The equivariance group becomes bigger and bigger. Okay, the previous method for building GENEOs can be generalized by replacing the arithmetic mean with an arithmetic function. Please consider that the machine to get GENEOs in this proposition is an average, a weighted average. But now we can say, what happens if we replace the average, the weighted average, with another symmetric function? The proposition is still true, since we can indeed show that when a symmetric function and the permutant for the equivariance group G are available, we can easily build a nonlinear, this is an important thing, now a nonlinear GENEO with respect to the same group G. In order to do that, in order to show that, we have to recall the concept of permutant, not permutant measure, permutant, which is related to the concept of permutant measure. Definition, we say that a subset of a group of permutations of X is a permutant for the group G is either H is the empty set or H is stable under the conjugation action of a group. In this setting, please remember that we are considering a finite set X. So this set H is finite too. Note that a subset H of a group of permutations of X is a permutant for G if and only if H is a union of orbits for the conjugation action of our group. Now, definition, I'm just recalling well-known definitions now. Let C be a symmetric subset of Rn, that is a subset C such that it is stable under every permutation pi of the coordinates. A function f from C to the real numbers is said to be symmetric on C. I see maybe, oh, sorry, just I'm reading just now a question. What is the difficulty in constructing GENEOs using R measures on compact group G? This is quite an interesting question. As you can see here, the theory has been developed at this time just for the finite case. So we are trying to extend the theory to compact groups, but I have no results to show for this case. Please think about this, that it is quite recent theory. And so for most of the question you can ask, I have no answer. Okay, let me check if I cannot see any other answer, but please, in case you have answer, stop me, since I cannot see the chat. Okay, so a function f from C to R is said to be symmetric on C if its value is the same no matter the order of its arguments. So this equality holds. For every A1, AN belonging to the set C and every permutation pi of set 1n. Okay, so this is the definition of symmetric set proposition. Let f be a continuous real-valued symmetric function defined on a compact symmetric subset of Rn. Then f is the restriction of a continuous real-valued symmetric function, f bar, defined on Rn. So in other words, the concept of continuous real-valued symmetric function defined in a compact symmetric subset of Rn coincides with the concept of restriction to this set of a continuous real-valued symmetric function defined all over Rn. Now, what happens if we have a symmetric function in place of a weight average? Let us call S this function. And so S is a symmetric function from Rn to R. Assume that we have a non-empty permutant H for the group G. Then we can define an operator SH by setting for any admissible signal phi, SH of phi equal to S of phi composed H1, phi composed Hn. The same definition that we have seen here, but when we replace the weighted average with a symmetric function S. So, okay, what happens? This SH, this function SH is a group equivariant operator with respect to the identical homomorphism. And if a restriction of S to this set is non-expansive, then SH is a GENEO. This set is just the set, you take for each admissible function, you take the image, and you consider the union varying the admissible function. And you take this set, time itself, n times. Okay? So now, if we have a symmetric function, not just the weighted average, we can build a GENEO. But now we have to say something about symmetric functions, something that you probably already know. It is a well-known theory, proposition. Let K be a compact and symmetric subset of Rn. If S restricted to K is the restriction to K of a continuous symmetric function, S from Rn to R, and we denote by this symbol the max norm referred to the domain K, then for every epsilon greater than 0, there exists a symmetric polynomial Q that approximate the restriction to S to K better than epsilon. Okay, this allows us to use, instead of symmetric functions, their approximation by symmetric polynomials. So up to this error, we can restrict our attention to symmetric polynomials instead of considering symmetric functions. Now, I would like to say something about symmetric polynomials, since they are interesting in this topic. You know that the elementary symmetric polynomials in the n variables a1, an, also called elementary symmetric functions, are defined in this way. The first symmetric polynomial is sigma 1, that is the sum of a1, an. The second symmetric polynomial is this one, and so on until we reach the nth symmetric polynomial, that is the product of a1, a2, an. Now, when we use sigma 1 in what I'm going to say, we obtained the weighted average. So the proposition you have seen previously. But we can use the other symmetric polynomials, and you still obtain equivariant operators. Now I have to recall an important result in the theory of symmetric polynomials. The fundamental theorem of symmetric polynomials states that any symmetric polynomial in n variables a1, an is representable in a unique way as a polynomial in the elementary symmetric polynomial sigma 1, sigma n. By grounding of this classical result, we can proceed this way. In conclusion, if an equivalence group G is chosen and the GEO F is built, F equal to SH, we can approximate F in the following way, provided that X and phi are compact. First of all, we can approximate the continuous symmetric function S by a polynomial P with an error smaller than epsilon on the symmetric set, on this symmetric set, which is compact under our assumptions. Then we can consider this symmetric polynomial Q obtained by averaging the values of P And finally, we can consider the group equivariant operator f prime defined by setting f prime of phi equal to q of phi composed h1, phi composed with hn. We get this inequality that states that f prime is an epsilon approximation of f. So we can restrict ourselves to consider continuous symmetric functions and symmetric polynomials. The fundamental theorem of symmetric polynomials guarantees that the restriction to this set of any continuous symmetric functions can be approximated arbitrarily well by the restriction to the set, the image of phi to the nth power of a polynomial in the elementary symmetric functions defined in this way. Okay, where am I? Okay, these are just technical details that I'll skip. We already know that the associated operator is a GEO, but we can indeed obtain a GENEO by considering a suitable multiple of S tilde, of this function. In order to do that, we need some constant. I skip the mathematical details, just focus on the way that we can define the constant C by this formula that refers to these three formulas. And when we have computed C, we can proceed this way. If you take the previous operator, that is a GEO, and you divide it by C, you obtain a GENEO. So we have a method to obtain GENEOs by applying this method based on permuted measures and symmetric polynomials. Now, how can we represent a linear GENEOs? In this paper on the finite representation of linear group equivariant operators via permuted measures, we have proved this representation theorem for linear GENEOs. Assume that we have a group that is a subgroup of a group of any possible permutations of a finite set X. And also assume that G transitively acts on the finite set X. Transitively X means that for every pair of points x1 and x2, you can find at least one element in the group that takes x1 to x2. Now, let us assume that f is a map from the set of any functions from x to r to itself. We can say that the map f is a linear GENEO from Rx to Rx with respect to identical homomorphism if and only if a permuted measure mu with respect to G exists such that f can be represented by this summation for every phi, and the total mass of a permuted measure is less than 1. So in other words, the other theorem, the other proposition that I have stated previously, it is not just a sufficient condition, it is a necessary condition. Okay, now let me explain something in my last 7 slides. Let me say something about the applications of a theory of GENEOs. GENEOs are tools to simplify information and to emulate the behavior of, let me say, simplifying observers. I'm going to speak about a toy example, first of all, and then I will speak about a real example. The toy example is like this. Think about comparing real dice and fake dice. We produced a large number of real dice where, you know, in real dice, you have that the sum of opposite faces is 7. We produce also fake dice where the sum of opposite faces is not 7. When I say we produced dice, we thought about the coloring of the faces, not just saying this face is 1, this face is 2, this face is 3. We have a face that is a colored image, okay? So we have a function that describes the coloring of the faces of one cube, and we produced functions representing real dice and fake dice. And what happens? After producing 10,000 dies, a training set of size 7,000 and the test set of size 3,000, we applied PCA in order to reduce each function, each coloring representing a die, to just 2 numbers. Okay, so each die is transformed by PCA to a pair of numbers that is a point in the real plane. Okay, so have a look at on the left. The orange points are the points corresponding to fake dies, and the blue points correspond to real dies. And you can see that they are mixed. There is no clear separation between fake dies and real dies. But if you apply a suitable GENEO, you obtain this picture on the right, where there is a pretty clear separation between the fake dies and the real dies. In this case, the GENEO did its work, the work of changing the data in order to make them more understandable for our GENEOs of a different level. Okay, for each die, the first principle, as I explained this, okay, the GENEO we used in this example was built by a convex combination, and you know the convex combination preserve the property of being a GENEO, of 3 GENEOs defined by permutant measures. Okay, so this is the toy example. Now a real example, a research that we are doing with as for proteins and drugs. So we have this preprint, GENEONet, new machine learning paradigm based on group equivariant non-expansive operators, an application to protein pocket detection. And we have proteins. On the left, you can see the protein 2QWE, and you can see pockets. What is a pocket? It is a place, a cavity, where some ligand, some drug can join the protein in order to change the action of the protein. And this is important for drugs, for developing drugs. So if you look carefully, you can see numbers in each colored pocket. It is the level of confidence that it is indeed a pocket where a ligand can join the protein. Okay. In order to do this, we used 8 different kinds of GENEOs. Each GENEO thinks about a channel of information, and there is a GENEO, there are GENEOs thinking about the geometry of the protein, other GENEOs thinking about the electrostatic fields of the protein, and so on, for 8 channels. Okay, and we consider the convex combination of these GENEOs, and we optimize the GENEOs in order to have a good localization property with respect to the identification of cavities of pockets. What is the result? In this diagram, the higher, the better. The blue line is GENEONet. The other lines are other state-of-the-art methods to locate pockets in proteins. And you can see that the result obtained by GENEOs are quite good. But what is the difference? The important thing, the important information is that GENEONet uses just 17 parameters, while a convolutional neural network such as the pocket is the green line, requires more than 500,000 parameters. When you are able to insert information in the structure, and you can localize the right part of information you have to consider, you can get better results. What is our plan in the future? In perspective, what we are trying to do is looking for a good compositional theory for building efficient and transparent networks of GENEOs. Some preliminary experiments suggest that replacing neurons with GENEOs could make deep learning more transparent and interpretable and speed up the learning process. Why more interpretable? Since we know what each GENEO does, if we have some knowledge about the process. And we try to insert this knowledge in machine learning. And that's it. I thank you so much for your attention.